Gnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture, we have used some basic results about groups, especially order of an element in a group. And in this lecture, I will digress on the simple facts about groups. So let us do digression. In groups. All right, so we will as usual denote G group, and we will use binary operation written multiplicatively. So we will keep saying that G is a multiplicative group. That means the binary operation in G is written as A times B or simply AB. So this is the binary operation in G, AB in G, then AB belongs to G. That is the binary operation in G. And now we want to define what is order of an element in G. So let A be an element in G, and HA, H of A, denotes the subgroup generated by A. That means this HA, so that is HA is power of A power n, as n varies in Z. This is clearly a subgroup of G, and by definition this HA is the smallest subgroup of G containing the given element A, and it is therefore clear. So clearly HA is therefore by definition intersection of all the subgroups H where A belong to H and H is a subgroup of G, and on the other hand this is one candidate A power n, n in Z. This is, as I said, this is clearly a subgroup, and all the powers therefore are contained in every subgroup. So therefore this equality here. So that is the smallest subgroup of G containing A. Now we define order of an element. Order of an element so A is in G, and let us denote E to be the identity in G. This is the neutral element, neutral in G, that is also called identity element in G. So order of odd A, this is the order of A. This definition is slightly different from the standard textbooks, but it is more useful than the standard one, and also it clarifies some ambiguity somewhere. So, order of an element is by definition, it is 0 if HA is not finite. Not finite, then it is order 0. And cardinality of H of A, if H of A is finite. So, order of an element is never, we never say it is infinite for many reasons. We never write this symbol. This symbol is not written because of its, first of all, it is not defined. Also, it is countable, uncountable, all kinds of problems will crop. So, we never define an element of infinite order. So, it is A power 0 is identity always, and A and so on. If these powers of A, they don't come back to identity, that means that this HA is not a finite group, and in that case we define order to be 0. Okay, so let us see few examples which will throw some light on our definition. Let us take G to be the additive group of integers under addition. 1 is in Z. Remember, identity element, neutral element is 0 here because we are taking the additive operation. So, what is the order of 1? Order of 1 is 0 because what is the subgroup generated by 1? That is the whole group G. This is the whole group G, which is not finite. Therefore, order of 1 is 0. Similarly, if I take any integer n, what is the order of n? That will also be 0 because if I take the subgroup generated by n, those are precisely the multiples of n. So, these are precisely an as a varies in integers. Multiples because our group structure is addition. Therefore, in both the cases, the subgroup is infinite, therefore, order is 0. All right. So, further now, when does we say that G is cyclic? If G equal to G is generated by one element, G is equal to HA for some A in G, and this element A, the element A is not unique in general, and is called a generator or also called a primitive element for G. For example, if G is the group Z plus, then G is generated by 1, also generated by minus 1. More generally, if G is arbitrary group, if G is generated by A, then G is also generated by A inverse. This is multiplicative notation and this is additive notation. Okay. So, if in this case, if n is an integer and n is more than 1, modulus of 1 is bigger than 1, then h of n is a proper subgroup of J. It will never be equal. So, this means there is no other generator than 1 and minus 1. So, Z, this means this Z plus is a cyclic group and 1 and minus 1 are the only generators for Z. Okay, so some more obvious remarks that now we know cyclic groups. So, what about non-cyclic groups? So, cyclic groups, first observation is cyclic groups are countable. That is clear because cyclic means it generated by one element, that is, it is the smallest subgroup which contain this A, but this is nothing but A power n, as n were the integers. So, therefore, there are at most z many elements in G. So, in particular G is countable. So, now if you look at the group R cross under multiplication, non-zero real numbers under multiplication or non-zero elements under multiplication, non-zero complex numbers under multiplication, these groups are obviously not cyclic because simply they are not countable. But now the group Q cross rational non-zero rational numbers under multiplication, this group, though it is countable, is not cyclic. This needs a proof, but this proof is not obvious, but also it is not so difficult. This follows from what is called fundamental theorem of arithmetic. Fundamental theorem of arithmetic, which one learns in the school, which says that every natural number is a product of prime numbers in a unique, essentially unique way up to a permutation. So, so that one can use that to prove that actually more general than non-cyclic, that Q cross under multiplication, this group is not even finitely generated. Let alone one element generating the non-zero rational numbers, but even finitely many elements cannot generate Q cross as a cyclic, Q cross as a group under multiplication. So, there are two kinds of cyclic groups as we have seen. G is a finite group, let us say G finite group. Then G is cyclic, that means G equal to H of A if and only if order of A equal to cardinality of G for some A. And that A will be a primitive element because this order by definition it is cardinality of this and therefore it is clear. So, that is in case of a finite group. When G is infinite group, then G is cyclic. If and only if G is isomorphic to the additive group Z plus. So G2 Z plus, there is an isomorphism. Then only it is cyclic. This is so infinite case there is only one group up to isomorphism, and finite case there are many more. All right. So how is this isomorphism done? So that is done as follows. More generally, what we do is the following: given any group G and any element in the group G, so this is arbitrary group and A is an arbitrary element there, then we have a map from Z plus to phi, the map phi, this goes inside H of A, which is a subgroup of G, and what is the map? Any n goes to A power n. So A power n is obvious. This HA is by definition A power n, n varies in integers. So therefore, we have a natural map. It is obvious that this phi is a group homomorphism. To check that, what do we have to check? That it phi respects the operations. So that means we need to check the equality phi of n plus m. You take two integers, add them, and then take the image of phi. On the other hand, you take image of phi, image of n under phi, image of m under phi, and multiply them in the group G, and whether this result is same or not. That is where one checks it's a group homomorphism. But what is this by definition? This is A power n plus m, and this is A power n, this is A power m, and the way we multiply elements in the group, the associativity of the group will tell, we can club, and this is equality then. So therefore, image of phi, this is a group homomorphism, and image of phi is nothing but the subgroup generated by A. So H of A. So that is how. And what is the kernel? Kernel of phi. This is by definition all those elements n in Z such that phi of n is the identity element in the group G, but this is same thing as saying that is A power n is identity element, but this is kernel is a subgroup of Z plus, this is a subgroup, but we know all subgroups of Z plus. Every subgroup of Z plus is of the form, they are Z multiples of the fixed number m. Moreover, if you choose, if m is a natural number, then it is unique, then it is uniquely determined. That is the unique generator, and this unique generator is called the order of, this is nothing but this m, unique m is precisely the order of the element A. And we know if I take Z, go modulo the kernel, this quotient group is isomorphic to the image of phi. This is precisely H of A. So the kernel of phi is generated as a subgroup of Z by order of A. All right. So, let us see some examples. So, just to get acquainted with how does one compute the order. So, let us take G to be the product group Z mod 2 with the modulo 2 operation cross Z additive group of Z. So, remember the operation here is modulo 2 operation and here the operation is usual addition. So, one look at the element 1 comma 0, this is an element in G, and what should be the order of 1 comma 0? I claim order of 1 comma 0 is 2. That is because, see, what is the 2 times, now it's additive group, so I will write 2 times 1 comma 0. This is by definition adding this element itself with itself. So, this is 1 plus 1, but it's a modulo 2 operation. So, the first component is 0 and second component is 2 times 0, that is 0. So, 2 times that element is 0 and this element is non-zero. This element is not identity element because identity element of the product group is identity in each component. So, what is the subgroup generated by 1 comma 0? This is nothing but only 2 elements 0 0 and 1 comma 0. So, this subgroup has cardinality 2, therefore, order of this is 2. This is precisely the cardinality of subgroup generated by 1 comma 0. Oh, what is the element of order 1 comma 1? So, for that again we will compute the subgroup generated by 1 comma 1. What will this be? So, obviously I claim that this subgroup cannot be the whole group simply because the element 0 comma 1 is an element here and 0 comma 1 can never be an element here, because to get 0 comma 1 you will have to multiply this element by some integer, but when you multiply this element the second component can never be 1 again. So, therefore, this subgroup is actually infinite. This subgroup is infinite because we can keep multiplying by n. So, you can get different, the second component is always different. So, therefore, this element has order 0 because this is this subgroup generated by that is infinite order. So, with this I will okay. So, then in the next lecture we would have discussed what is the structure of the unit group of a field, that we wanted to prove that if you have a finite subgroup of the unit group of a field, then it is cyclic. This is proved in couple of lectures later. Okay, all right. So, next thing I want to do now is 8. Now, another thing I used in my last lecture was what is called Lagrange theorem. So, let me state it first. So, G be a finite group and H is a subgroup of G, then the order of H divides order of G. This is how it is stated, how the theorem appears like this in normally in every textbook on the elementary group theory. However, Lagrange didn't come to this statement in this way. Lagrange came to this statement by computing the fixed points of some group action. So, but this is very easy to prove. This is more of a set theory than a group theory. So, how does one prove? Proof. So, given a subgroup H, using H, we define a relation on G. What is the relation defined? That means, suppose I have two elements A and B in G, then I will say that A and B are related under this if and only if, this is a definition, B inverse A belong to H. Now, one really easily verifies that, check that this is an equivalence relation on G. Equivalence relation means you have to check three things, namely reflexivity, transitivity and symmetry. And I will not go into this detail. So, reflexivity simply means that A is related to A, that means A inverse A belong to H, which is very clear because A inverse A is identity element. Similarly, symmetry and similarly the transitivity. So, I will leave it for you to check this. So, this is a check that it is a equivalence relation on G. Okay. Now, once you have equivalence relation, one talks about the equivalence classes. So, what are the equivalence classes? So, what is the equivalence class of A? Given A in G, equivalence class of A under this equivalence relation is, it's also denoted by A, suffix this notation of the relation. This is by definition all those elements B in G such that A is related to B, but this is equivalent to checking that B inverse A belonging to H, but this is same thing as B belonging to the coset AH. So, therefore, this equivalence class is nothing but the left coset by H. This is the left coset of H by A. This is precisely all those elements of the form A times H, H is in H. So, note that the left coset AH and the subgroup H, they are in bijective correspondence with each other, and the bijection is simply given by H going to A times H. This is clearly bijective because the inverse is given by A inverse. So, inverse is given by any AH here, multiply by A inverse. So, you will get 2H. So, this is multiplied by A inverse, this is multiplied by A. So, therefore, they are inverses. So, in particular cardinality of the left coset and cardinality of the subgroup, they are same. So, all right, once we have this, then Lagrangian theorem proof is more or less clear because look, so what does the equivalence relation and equivalence classes do? Therefore, this G is decomposed as a disjoint union into the equivalence classes. Equivalence classes are the left cosets. So the union, this disjoint union is varying over all the elements A which are in the, this is the number of cosets of H in G. This is precisely the quotient set of G by the relation this. So G by H is precisely the equivalence classes. And you only take the different, collect only those elements which have the different equivalence classes. So therefore, cardinality, G is finite, so this is a finite set and this is a partition of the finite set. Therefore, cardinality of G will be equal to the sum. Sum is running over the set, quotient set G by H, and the cardinality of the cosets. But we have seen cardinality of the coset is same thing as cardinality of H, and this sum is varying over G by H, and this is a constant, so I can take it out, and so therefore this is equal to cardinality of H times cardinality of the quotient set G by H. So we get a formula, cardinality of G equal to this. But from this formula it is very clear that order of H divides order of G. So that proves Lagrange's theorem. Okay, now only two observations I have to record for the future use. So corollary 1, G finite group, and I have an element A in G, then order of A divides order of G. Proof. What is the order of A? So, given any A in H, we form a subgroup generated by A which is HA, and G is finite given. Therefore, every subgroup is finite. Therefore, order of A is by definition order of H of A. This is the cardinality of H of A. But then Lagrange's theorem says that this divides order of G by Lagrange's theorem. So that means order of A divides order of G. So in this case, what will be H of A? H of A is clearly identity A. You can go on till A power order of A minus 1, and the next power will be identity. So this is precisely the subgroup generated by A. All right. So second corollary is what is known as Fermat's little theorem. Fermat's little theorem. Okay, what does it say? If G is a finite group, A is an element in G, or A is an element in G, then A power order of G equal to identity. Proof. So let A be in G. Then as usual we know what is H of A. H of A is a subgroup generated by A. This is obviously cyclic subgroup of G because it is generated by A, and the order of this group, order of H of A is by definition order of A, because we are in a finite group. So H A is also finite. Therefore, as I said, H of A is nothing but E A powers of A going on till A power order of A minus 1. This is precisely H of A. And what is A power the next? A power order G, that is what we want to prove. But order of A divides order of G. So A power order A times some integer m. But A power order A is already identity. A power order A, this power m. But this is already identity. So it is E power m, which is E. So we have proved A power order A is identity. So just one little one can also prove this in a slightly different way. So second proof, okay, so G is this I give proof is given, that proof doesn't use the fact that G is abelian, but this proof is for finite abelian group. So G is finite abelian. Okay, and A is an element is given, then I consider the map lambda A on G. This is a left multiplication by A. So this is any x going to AX. This is clearly a bijective map. This is bijective because the inverse of this map, in fact we can write it down. This is nothing but lambda suffix A inverse. Inverse is given by that. So any y going to left multiplication by A inverse y. This is the inverse map for this lambda y. So now let us compute the product x in G. This is same thing as product x in G. Instead of x I will write AX, because it's a bijective map. This product has not changed, so it is a bijective map. And because G is abelian group, this A is coming as many times as G. So this is A power order of G times product x is in G. But you see this element and this element, they are same. This element equal to this element, they are same. Therefore, and they are element in a group, so I can cancel it. So that will prove that when I cancel this element, I will prove that one gets that E equal to A power order G. This is what we wanted to prove. So this proof uses obviously the fact that G is abelian, because I have taken out A so many times to write this. So here I use the fact that G is abelian. Alright, so with this I will stop this digression on the groups, and it is further continued to study more groups later on. And I will prove later that if I have a finite subgroup of the multiplicative group of a field, then it is cyclic. In particular, Z mod P cross this group is cyclic. This is proved later in the lectures. Thank you.